back to our pizza example. What if we had 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce? How many pizzas can we make? I hear 3, I hear 4. How can we figure it out? Well, what we need to do is find out which one of these things we're going to run out of first, right? So we can look at the number of crusts and figure out how many pizzas would that make. And we can look at the number of cups of cheese and figure out how many pizzas would that make. And we can look at the sauce and figure out how many pizzas if I use up all the sauce, right? And so you can kind of do that in your head, but let's write it down, so 4 crusts. And we get 1 pizza for every crust. It's kind of a no-brainer. So if we use up all the crusts, we could make 4 pizzas. Tomato sauce, 15 ounces, and we get 1 pizza for every 5 ounces. Ounces cancel out. 15 divided by 5 is 3. So when I make 3 pizzas, I'm going to run out of sauce. Can I make more? No, I can't. So could I make 4 pizzas? No. Well, let's check the cheese. 10 cups, 1 pizza per 2 cups of cheese. So that would give us 5 pizzas. So how many pizzas can we make? 3. So the process here, we're going to be doing with this with chemicals in a minute. The process here is we take the different ingredients that we're given and we figure out how much of the product we could make from each of them. And then we look at those answers and we say, well, which is the smallest one? The smallest one is 3 pizzas. And that is the answer to how much product can be made. Because what's going on here is as you're going along, you make a pizza, you make another pizza, you make another pizza, you get to this smallest number. When you hit that, you've run out of one of the ingredients. I'm out of sauce, so I have to stop. That's the end. Any questions? Does that make sense? So it makes sense when we're talking about pizzas, right? When we do it with like octane and CO2 and stuff like that, people lose their minds and they do all sorts of crazy things. Like they'll do this very nicely, do all the equations and all the math, and then they'll take these numbers and add them together and say, I can make 12 pizzas. What? No, you can't. That's ridiculous, right? Once you get to 3, you have to stop because you ran out of something. So here we would say that the amount of sauce is limiting our production, right? It limits the number of pizzas. If we had more sauce, we could make more pizzas. So here it is in pictures. 4 crusts would make 4 pizzas. This amount of cheese would make 5, but the sauce will only allow us to make 3 pizzas. So we call this the limiting reactant. It is the reactant that gets completely used up. It is very, very unusual in a chemical reaction, as it is in the kitchen, for you to have exactly the right amounts of every single ingredient. Because if you're going to make pizzas, you know, the amount of cheese is not necessarily, you can't necessarily purchase it in exactly the right amounts. And the sauce comes in a container and you don't control exactly how much you have. And so you're going to run out of one thing before you run out of other things. And that happens in chemical reactions as well. This least amount of product is what we call the theoretical yield. If everything works like it's supposed to, that's how many pizzas we're going to make. So tomato sauce we would call the limiting reactant or the limiting reagent. It's whichever ingredient makes the least amount of product. The maximum number of pizzas that we can make is the smallest of all those numbers we calculated. That's called the theoretical yield. So in chemical reactions where we have multiple reactants, it's very, very common that one of the reactants gets used up. When that reactant is used up, just like making pizzas, the reaction stops. No more can happen. And so that reactant limits how much can be produced. The other stuff is not completely used up. There's extra. And so that's called excess reactants. So one of them gets used up and the rest are in excess. Well, the actual amount of product is called the actual yield. So there's the theoretical yield and there's the actual yield. The theoretical yield is what could we get if everything works perfectly? Have you ever made pizza or pancakes or something and you drop one on the floor? Or you get distracted by your video game and you don't hear the timer and you burn one to a crisp, right? So you only made 2 pizzas because you burned one. Is your actual yield 3 pizzas? No, it's only 2 because that one was unusable. In theory, you should have been able to make 3 pizzas. You had enough stuff, but you screwed it up, right? In chemical reactions, stuff happens as well. And so we don't always make exactly the amount that we think we're going to. So we typically express how well the reaction goes as a percent yield. Use percent yield to express the efficiency of the reaction. So percent is the part over the whole times 100. Here the part is how much we actually made divided by the theoretical yield, how much we could have made in theory, times 100. So if you make 2 pizzas and you should be able to make 3, 2 divided by 3 times 100 is 67%. Which, if you're working in a pizza restaurant, they're probably not going to be happy with 67% yield. They're going to want it much closer to 100. So this is a summary of all those terms. Limiting reactant, excess reagent or reactant, the theoretical yield, the actual yield, and the equation for percent yield. So let's apply these concepts to chemical reaction. So we looked at this one when we were talking about how to balance equations. So here we have 1 methane molecule and 2 oxygen molecules, and here we're going to make 1 CO2 molecule and 2 water molecules. So if we have 5 molecules of methane and 8 molecules of oxygen, which one is going to get used up first? We're going to do the same sort of calculation we did for the pizza. So if we have 5 molecules of the methane, well, how many CO2 molecules can we make for every methane molecule? Well, it's 1 to 1. So for every methane molecule, we get 1 CO2 molecule. So we could make 5 CO2 molecules. Eight molecules of oxygen. We don't have the equation here anymore. That's no good. How many moles or molecules of CO2? Let's go back and look at the equation. So it takes 2 oxygen molecules to make 1 CO2 molecule. So 1 CO2 for every 2 oxygens. This is like the cups of cheese, right? So if we have 8 oxygen molecules, we can only make 4 CO2 molecules. So using up all the methane, we could make 5, but using up all the oxygen, we can only make 4. So we can only make 4 molecules because we run out of oxygen. And when that happens, the reaction stops. So the theoretical yield here would be 4 CO2 molecules. Any questions? So that's looking at the particles, but of course we want to look at masses because that's how we measure things. So there are different ways to approach these problems, and I will do one way, and because I think it's a good way. If you like a different way that works for you, that's absolutely fine. This is what your book talks about. So you start with the mass of each of your reactants, you calculate the moles of the reactants and then the moles of the product, and then they say, well, stop here and look at which one of these is smaller. Take the smaller one and then convert to product. So that is entirely valid. What I'm going to show you, because it requires less thinking, is just do two identical, well, almost identical calculations. Grams to moles to grams for one reactant, grams to moles to grams for the other reactant. And then, which is smaller? That's your answer. Okay? So that's my approach. If you like the book's approach, that is fine. That works too. Okay, let's do an example. What's the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? And we're given a balanced chemical equation here for the synthesis of ammonia. I'm going to use my chemical equation to organize my information. 5.22 kilograms of hydrogen, 31.5 kilograms of nitrogen. We cannot just look at this and say, oh, there's a lot less hydrogen, that must be limiting. Because the masses of nitrogen and hydrogen are very different and the mole ratios are different, and you can't just look at it. You have to do the calculation. So here again, we have the grams and the kilograms business. Did you like setting the kilo aside and just doing grams? Did that make sense to you? Okay, so we're going to do that again. We're just going to set the kilo aside, and we'll bring it back at the end. So what I want to do is I want to take this mass of hydrogen and go grams to moles to grams and find the mass of ammonia. This is what we're trying to find, how many kilograms of that. Separate calculation, I'm going to do the nitrogen, grams to moles to grams, and find the mass of product. Okay? Then I'm going to look at those and say, which one's smaller? That's my answer. And I'm done. Okay, so 5.22, there's our kilo that we're just going to let sit there, kilograms of hydrogen. So I want to go to moles of hydrogen, so moles of H2, and I'm going to divide by grams of H2 to cancel out the grams. Grams to moles. Next I'm going to go to moles of ammonia, and I'm going to be dividing by moles of H2. And then I'm going to go to grams of ammonia, dividing by moles of ammonia. Any questions? Mole to mole ratio comes from the balanced chemical equation. There's a 3 in front of H2, so I'm going to put a 3 in front of moles of H2. There's a 2 in front of NH3, so it's 2 moles of NH3. I need the molar mass of oxygen. That's 2 times 1.008, so 2.016. And I need the molar mass of ammonia. And since this is not about showing you how to do that calculation, I'm just going to write it in there, 17.034. So I'm going to do the math. 5.22 divided by 2.016 times 2 divided by 3 times 17.034 equals. I should have three significant figures. 29.4, there's three sig figs, 03, and I still have that K because it didn't cancel out, kilograms of ammonia. So that's one possible answer. We're going to do a very similar calculation using the other reactant. Grams to moles to moles to grams, just with nitrogen instead. So 31.5. Again, we'll just set that kilo aside. So kilograms of nitrogen. We're going to the same product. So we're moles of nitrogen divided by grams of nitrogen. And then we're going to go to moles of ammonia. Divide by moles of nitrogen. Those units cancel out. And then we'll go to grams of ammonia, dividing by moles of ammonia. This last term is the same for both of them. So there's just really no thinking there. This is one of the reasons I like this method. It's not really any extra work. We'll just write that down. Mole ratio again, from coefficients, 1 mole of nitrogen makes 2 moles of ammonia. 2 moles of ammonia for every 1 mole of nitrogen. The molar mass of nitrogen, 2 times 14.01, so it's 28.02. So 31.5 divided by 28.02 times 2 times 17.034. This should also have three significant figures. 38.299. And let's not forget my kilo that didn't cancel out. Kilograms of ammonia. Anybody checking my math? Looks right, thank you. How much ammonia can I make? Which of these numbers is smaller? The first one. So this is how much I can make, right? So that's going to be my answer. So I'm going to round that and say 29.4 kilograms of ammonia can be made. Any questions? I can't make any more than that because when I get to this mass, I run out of hydrogen. It's like running out of pizza sauce. It stops. The reaction stops. Okay, here's another one. Lots of examples. These are important calculations. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams of iron. Determine the limiting reactant, the theoretical yield, and percent yield. So, slightly different than the last problem. Again, use the chemical equation to organize your data. So, Fe2O3, I've got 167 grams of that. I've got 85.8 grams of carbon monoxide and 72.3 grams of iron. Where's my question mark? What are they asking me for? So they want the limiting reactant. So in order to do that, we have to calculate the amount of product and find out which is smaller. They want the theoretical yield. That's the amount of product that can be made. And then they want the percent yield. Percent yield is the actual yield divided by the theoretical yield times 100. So we can't do that one first because we don't know what the theoretical yield is. So theoretical yield is what I need to calculate first. There are two products there. Which one are we interested in? Why is the mining company doing this reaction? They're trying to make CO2? No, they're trying to make iron. They're trying to get iron, right? So this is the compound, this is the product we're interested in. But we have a number there. So there's an actual yield and a theoretical yield. If you set out to make pizzas, we can calculate how many in theory you can make. How do we know how many you actually make? You have to do it, right? And see what happens. Who knows what could happen when you're making pizza, right? So the actual yield has to be given to you. So this is saying this reaction produces this much. This is the actual yield. So this is my actual yield. So I don't really necessarily want that here because I need to find out what the theoretical yield of iron is. I've been given masses of 2 reactants. That tells me I've got a limiting reactant problem. Any questions yet? So I need to do 2 calculations, one going from this reactant to a mass of iron, and the other going from this mass of reactant to a mass of iron. And then I'm going to find out which one is smaller, and that is my theoretical yield. Okay, so 167 grams of Fe2O3, grams to moles to moles to grams. So grams of Fe2O3 to moles of Fe2O3. And grams go in the denominator. And then I need moles of the product I'm interested in, moles of iron. I'm going to divide by moles of the iron oxide. And then I'm going to go to grams of iron, dividing by moles of iron. Grams to moles to moles to grams. Moles to moles comes from the equation. 1 mole of Fe2O3 would produce 2 moles of iron. Molar mass of iron is easy, it's just on the periodic table, 55.85. I need to calculate the molar mass of Fe2O3, 2 times 55.85 plus 3 times 16. $159.7. Thank you. So 1 mole weighs 159.7 grams. So 167 divided by 159.7 times 2 times 55.85 equals. I started with 3 significant figures. Everything else is at least 3, so this will have 3. 116.80 grams of iron. So then I need to look at the other reactant. So 85.8 grams of carbon monoxide. Same type of equation here. So I'm going to go to moles of carbon monoxide dividing by grams. And then I'm going to go to moles of iron because that's what I'm trying to find out about. And then grams of iron at the end. So that last term again is the same, 55.85. I need a molar mass for carbon monoxide. That's going to be 12.01 for carbon plus 16 for oxygen. 28.01. So 85.8 divided by 28.01. Oh, I forgot my mole ratio. So iron is 2 and CO is 3. So I have to multiply by 2 and divide by 3 and multiply by 55.85. 114, again 3 sig figs, 0.05 grams of iron. What is my theoretical yield? What's the most I could possibly make? The 114. It's the smaller one. So my theoretical yield is 114 grams of iron. That's the answer to one of those questions. They want to know what is the limiting reactant, the thing that's going to be used up. So I've identified the smallest amount of product. I just trace this back to the beginning and see which reactant gave that to me. It was the CO. So carbon monoxide is the limiting reactant, often just LR. Limiting reactant is the carbon monoxide. And then we need to calculate the percent yield. So percent yield is the actual yield over the theoretical yield times 100. The actual yield was given to us, 72.3 grams. The theoretical yield is 114.05 grams times 100. The grams cancel out. I'm using my unrounded value there because I want to avoid rounding errors. 72.3 divided by 114.05 times 100. So this should have 3 significant figures. So 63.393%, call it 63.4%. Percentages should not automatically be rounded to the nearest whole number. I've been seeing that in your labs. Significant figures tell us where to round them. So this reaction has a 63.4% efficiency rate. So the mining company might want to look at the conditions under which these things happen and say, well, how could we make that better? All right. Any questions?